Good morning, students.
Morning, sir. Morning.
All right, morning. All right, so we're still on statistics. So today we're dealing with statistics of group data.
Sir,
Yes.
sir, when you do statistics, and them give you a set of data, say, and would upon the exam, so they would have give us like a set of data, say, for statistics until we put it in the different frequency distribution, say, tables like the pie chart, bar graph, line
Yeah,
graph.
they can ask you anything. They can ask you anything. Just put it that way.
Oh,
And you see them will start doing questions, right? So don't worry about what they'll ask and what they won't ask. You will know and you will learn what they will ask from the questions that we will do, that we will practice.
Oh,
It's just a matter of understanding the information, learning the information, learning the methods, understanding that there are three different types, three different ways data can be presented. And the method that you use for the various statistical averages and measures of spread depends on the type of data that you have. With some of the data, you can calculate actual values, exact values, and some of it you have to estimate. So for example, on the slide here, you see me have why is it not moving? Right. You see me have the word estimate. Right here, estimating mean. When we did raw data, it was a matter of calculating the mean. When we did ungrouped data, it was calculating the mean. But now, because the data is grouped, the mean has to be estimated. Almost everything has to be estimated. And Josh said it in the last class, that when the data is grouped, you don't know the actual values. You only know the range of values. So you don't know the actual values when the data is presented grouped. And so everything you do is estimating. And then there are various estimation methods that are accepted. So the best estimation methods that we are going to use are the ones that are on your syllabus. All right, in fact, we're starting one right now. All right, so as I was saying, the important thing is to note that the method that you use depends on the data that is presented to you. And you have to be able to see those differences. So if I give you raw data to do mean, mode, median, range, interquartile range, then the method is different from if the data was ungrouped and in a table versus when the data is grouped in a table as well. The method is different. And now we're focusing on grouped data. All right, I looked at that in the last class. So persons, you just need to look back at the video of the last class to see when the need arises for group data and also some of the properties of a group frequency distribution table.
So you could send the recording later, sir, for yesterday.
I think I sent the recording already on the last class, on Wednesday's class. It's there.
Oh, no, sir, I was talking about yesterday, sir. If you could send that recording.
I didn't send that one as yet. All right. So yesterday we just did some revision. I'll send it, no problem.
Yes.
All right. So let me come off camera so we can get cracking with this thing. All right. So tomorrow is gonna be like a practice day. So we'll be mainly practicing questions tomorrow. So today we're finishing off with the notes, the statistics notes. Maybe tomorrow I'll do the summary, right? I'll do the summary thing tomorrow because I want to practice a few questions today on the group data. All right, and then tomorrow practice some more. So on Wednesday we'll be looking to do the classwork on this topic on Wednesday, so we can start a new topic on Sunday next. All right, so that is the plan. All right, so let me come off camera and we'll get into it. Okay. All right. So now we're looking at group data, and the first thing we want to do is estimate the mean. And note I don't want to calculate the mean, as I just explained. You have to estimate the mean from group data. So what is the concept? What is the principle behind it in terms of the approach? Firstly, this is estimated by using the class midpoint to represent the classes. Because we don't know the actual value, we're not going to know the actual values, right? That are scored because the data is grouped. What you do, you estimate, you assume that all the data in a group carry the midpoint value. That's what you do, right? You carry the midpoint value. So you use a class midpoint to represent the group. And then you come back to using that formula. Same formula for ungrouped data. Sum of fx, where fx is sum. Fx is the sum of the data divided by the number of data, which is the sum of the frequency. We're using that same formula, just that enough, because the data is grouped. The x value that we're using is going to be the class midpoint. Using the class midpoint as the value. So it's like you convert a group data into ungrouped data, but you're using a class midpoints. All right, so you can't use all of the values in the group. You have to use one value. So the value that you use from a group to represent a group is the midpoint value. So see there, x is the midpoint, x is the class midpoint value, f is frequency, fx is the sum of the observed values. That's what f times x is. I'll explain to you in an example just now. And n is the number of observations. So in this example here that you're looking at, let's say this is a mass of some cows or something, I don't know, mass of some stuff. And the data is grouped. So between 35 and 39 kilograms, there are 12 observations, 12 things. So these are the masses of some balls, right? Some metal balls. And these are the mass. And so what this is saying is that 12 of them measure between 35 and 39. But the problem is that you don't know the actual measurement. Maybe none of them don't measure 35 and none of them don't measure 39. But remember, you can take values in this range from actually 34.5 up to less than 39.5. So you can, that's what 35 to 39 really means. You can take values from 34.5 up to less than 39.5. Less than 39.5. And as I said, the problem is there are 12 observations in this group, but you don't know the actual observations. Same thing is happening here. There are 8 observations in this group, but you don't know the actual. You don't know if any actually measure 40, 41, 39.6, 44.2. You don't know the actual measurement. You just know that there are 8 of them. Same thing here. 10 of them in this group and 7 in this group. And so there's a total of 37 observations. 37 things were measured.
So sir, right? This is ungrouped, right?
This yeah, man.
Ungrouped data, this, sir, right, sir?
No, this is grouped. See, the values are grouped. The values are in a group. That's what we call group data. Ungrouped data is if them put the 35, 36, 37, 38, 39, 40, and all the way down. But what happened? We're going from 35. We're going from 35. We're going from 35 down to 54. So if we were to list them individually like this, the table would be extremely long. And so because the table would be extremely long, and a lot of them will be coming out with zeros, right? It makes sense to group the data. So you set a group from, and you try to make all the groups equal. So you set a group from 35 to 39, and count how many in that group, 12. Then set a group from 40 to 44, how many in that group, 8. Set a group from 45 to 49, and continue like that. So this is group data. You group it. You group the observations. That's what we call it grouped frequency distribution, because the data is grouped. But the problem, as I said before, let me repeat again. The 12 observations in this group, you don't know the actual observation, but you want to estimate the mean. So the best way to estimate the mean is say, okay, since I don't know the actual observation for that group, I'm going to use the midpoint value for this group. I'm going to use a midpoint value for that group as the observation and assume that all 12 measure the midpoint value, which is 37. I'm going to assume that all 12 of them measure 37. But maybe none of them really measure 37. Maybe 2 of them measure 37. You don't know. And that is why we're estimating the mean. And that's why the mean that we get is not really the true mean, because it is unlikely that all of them would measure 37. But that's what you're assuming for the purpose of estimating what the mean is, right? And so we need a class midpoint. So when we get the midpoint, for each value, that becomes our x that we need to put in this formula. See there, that's the midpoint values. So these are the midpoint values now, right here. So put in our midpoint values and it becomes the x values in this formula, right? So these are, so the midpoint of these is 37. As you can see, the midpoint of these is 42. And look here, these values going up by 5. Look at it, they're going up by 5 from class to class. So the midpoint values also will go up by 5. Simple as that. So why not I calculate the first one? I'll just keep adding 5 to get the rest of them, because I realize that these values increasing by 5. And class width is also 5, you know. Class width is not 39 minus 35, you know, because that will give me 30, that will give me 4. That is not the class width. The class width is 5, because it is 39.5. The upper boundary for this class is 39.5. minus the lower boundary for this class is 34.5. So I'm subtracting 34.5. And so the class width also is 5. So everything's symmetrical in terms of the spread of the data. Right? Everything's symmetrical in terms of how the data is presented, giving them to you in intervals of 5, really. All right. So these are the midpoint values. So what are these values now? Now, this value over here is the product of this and this. Why is that? Because what we are now assuming for the purpose of estimating the mean is that all 12 measure 37. We're assuming that 12, so that is balls. We're assuming that all 12 balls measure 37 grams or kilograms. So the total mass of that 12 balls is this, 12 times 37. So this is a sum. Remember, to get the mean, you know, you want the sum of the mass of all the balls divided by the number of balls. Or you want the sum of all the sum of all the observation, all the masses divided by the number of mass, or let's just say balls for simplicity. So you want the sum of the mass of all the balls, which is 37 balls, divided by the total number of balls, 37. So 12 balls, assuming that 12 balls, each of them measure 37. So the total mass of those 12 balls right now is this. And then the 8 balls in this group, you're assuming that all of them measure 42, which is not necessarily true. And the total mass of those 8 balls is 8 times 42, which is this. You're trying to find an easy way to add up the mass of all 37 balls. And then the 10 balls here, you're assuming that all 10 of them measure 47 kilograms. This is kilograms too, you know, this is in kilograms, the midpoint. So the total mass of those 10 balls is 470 kilograms. And then you have 7 balls left in this group, and you're assuming that all 7 of them measure 52 kilograms. 7 times 52 is this. So this becomes the mass of the 7 balls. So when you add up all of these, you're getting the total mass of all 37 balls, which is this figure down here. Understand that, guys?
Yes, sir.
Understand?
Yes, sir.
Yes, sir.
But I have understanding now, because we're adding up the mass of all the balls gradually. We measure the total mass of the 12 here, so because we assume all of them are 37, the total mass of that 12 is 444. Then the 8 here, so each of them measure 42, so the total mass of this 8 is this. 8 of them more gone in. Then you have 10 balls here. Each of them, you assume each of them measure 47. So the total mass of those 10 balls is 470. And then you have 7 balls left. Each of them you assume measure 52. So the total mass of those 7 balls is now 364. So therefore, the total mass of all of the 37 balls is the sum of this. That's what we call it, the sum of fx. So you sum the sum column. This is a sum column. Fx is your sum column, sum. You're trying to sum the masses of all the bars in a quick and efficient way. That's why I set up that FX column. So this represents the sum of all the 37 bars, and there are 37 bars in all. So it means that the mean mass, the estimated mean mass, is the sum of all the bars, the sum of the mass of all the bars divided by the number of bars, which is 37. So that's how you calculate the mean, or estimate the mean. See there? 1614 over 37. I wrote that down. And see, I give my answer in kilograms. Kilograms. That's how we estimate the mean when the data is grouped. You have to remember, guys, when the data is grouped, you're using the midpoint value as the value for all. You're assuming that all of them in the group measure the midpoint value, which is not necessarily true. In fact, it's more than likely not true. Not true. Not all of them going to measure 37 in the first group. Not all of them in the second group going to measure 42. Not all of them going to measure 47. But you're using those values for the purpose of estimating the mean. You have to understand that. And here's the wicked thing about it now. CSEC will ask you that very question. They have done it in the past. They ask a question like, why is this an estimated mean and not the true mean? They ask that, you know. Why is that mean that we calculated there an estimated mean and not the true mean? Somebody tell me, why is this mean that we just calculated a while ago? This mean that we just calculated over here. Why is it an estimated mean and not the true mean? Somebody tell me.
Because not all the balls in the group, sir, are of one mass. They could be of different masses from the 35 to 39 or from the 40 to 44. So not all of them are 42, but some of them could be 43 or 41 or 41.7. And what we did was to just assume that all the we assumed all the balls were 37, 42, 47, and 52 in the various groups and used them to find the mass.
You have said it. You have said it. Yeah, man, that is good. So you have said it. So that is correct. What you have said is just no matter of how you put it down on paper, right? Just a matter of how you put it down on paper. So these are things that you want to maybe write out and write it again and write it again until you say it in a clear way. So if you're in the exam and they ask that very question, you don't have to be guessing and writing too much and trying too hard to explain. So this is something that you want to write down as a reason and send to sir and say, sir, would this be okay? Could I tell them this? Would this be enough? Right? So you have answered it correctly, right? But you don't want to be there writing. Because most times a question like that might value 2 marks or maybe 1 mark. When I say explain, but you want the 1 marks, 1 mark is nothing, right? We want every mark in it. So let's not get into this thing of believing that 1 mark is not plenty. As most questions value 1 mark anyway. And if you keep giving away one mark, then you're going to end up with very little. So anyway, your explanation is correct. So I would say something like, this is an estimated mean because we assumed that the mean of all the balls in a group was equal to the midpoint mean. Or the mass, not mean, mass. Let's go again. We're saying that this is an estimated mean of the mass of the bars, 37 bars, because we assumed that in each group or in each class interval, all the balls in a class interval measure the midpoint mass of that class interval, which is not necessarily true. In fact, you can say which is not true. It is not true that all the balls in group 1 measure 37 kilograms. It is not true that all 12 balls. So for example, you can give an example to reference as you were doing. you're basically giving some examples. So you can pick a group and give it as an example. So you can say, for example, in group 2, in the 40 to 44 group, we assumed that all 8 balls in that group measure 42 kilograms, which is not true. We don't know the actual measurement of the 8 balls, but we assumed that all 8 balls in that group measure 42. And this is why the mean we calculated is not the true mean, it is just an estimated mean. Is there anybody in the class who don't understand what we have said? Anton said the correct thing, and I think I repeated basically the same thing that he said in a different way. Is there anybody in the class who don't understand, or somebody else want to explain it for me? Somebody else want to take a shot at it, of saying what you would say in an exam if they ask you, why is this an estimated mean and not the true mean? Anybody? All right, so since nobody wants to, let me call. Ajane, come, tell me what you would say, or you would say it. Ajane. Ajane.
Sir, I don't know.
So tell me what you understand. Tell me what you, why is it not a true mean? I don't know. So tell me why is it not a true? Look here, that's what I don't want in the class, you know, guys. I don't want you to sit there in the class, don't understand something and don't say anything. You have to give me an opportunity to explain it to a point where you understand it. Because when you understand it, you'll be able to answer the question. Right? Even if they come and they change it up and stuff. The key thing is not just knowing what to do, you know, it's to understand what you're doing. When you understand what you're doing, then you will know what to do even better. I don't want any student just know, so I do this, I do this, I do that. And that's how a lot of persons learn statistics. And a lot of, and not just statistics, a lot of the topics, people just know, say, do this, I do this, I do that, and I don't really know why. I want you all to know why you do the various things. Right? So come on, man, tell me, do you understand? Do you understand why this is an estimated mean and not the true mean of the data? Do you understand? As your name asking.
Sir, can you explain it again one last time?
All right. Someone listen to me good now. And everybody listen to me good. It's very important. All right, so let me go back. Let me go back. So they give us this data right here. These are the masses of some balls. So they took 37 balls, and they measured the mass of the 37 balls, and they get various masses. If they were to list the mass of each ball in a table, then they will get a table that is 37 rows long, a long table. If they were to list them and put 35, 36, 37, 38, these are the masses. And they want to put the frequency, how many balls measure these masses. And you're going to go all the way down to 54 kilograms. Not 36, yeah. If you were to list them like this, because usually you don't miss any. So for example, if none measure 39, the frequency would be 0. We tend to list all the masses down to 54. So that's to be the length of that table, 54 minus 35 plus 1. That's the number of rows that you have to put in there. So the table would be too long if you were to list it like that. If you were to do it ungrouped. Understand that so far? That's why you don't want to list it that way. Good. So you don't want to list it that way. The table going to be too long. So you want to do it in a more convenient way. So the more convenient way is to group the masses. You put them in groups. So those who measure between 35 and 39 kilograms, you put them in that group. Those that measure between 40 and 44 kilograms, you put them in that group. Those that measure between 45 and 49 kilograms, you put them in that group. And those that measure between 50 and 54 kilograms, put them in that group. But note also that this group can take any mass. Let's put X as a mass for now. That is greater than or equal to 34.5. Let me write it properly. It can take a mass. Any ball that measure 34.5 up to less than 39.5 can fit into this group. Tell me if you understand that. This
Yes,
is
sir.
measurement data now.
Yes,
Good.
sir.
Because 34.5 is approximately 35, don't it?
Yes, sir.
Don't it? And 39.5 is approximately 40, you know. That's how we say less than. It has to be less than 34.5, 39.5. Because if you put 39.5, it don't fit in that first group. Because that first group, you want it to stop at 39 to the nearest whole number. So therefore, the 39.5 is what starts the next group. That's why the second group now, the second group here, will take values from 39.5 now, less than or equal to X, but less than 44.5. So any value that is 39.5 all the way up to less than 44.5 can fit into that second group. But understand that?
Yes, sir.
Good.
Yes, sir.
And if you notice, that is why the groups share the same boundary. So this value share the same boundary with this value. And that's why the data is what we call continuous. It continues from one group seamlessly into the next group because these two values are the same. That's how we say the data is continuous. It continues, the values continue from where exactly where it leave off for one group, it continues in the next group. And that is why when you draw the histogram for this data, you have to put the bars side by side. You have to put the bars side by side. Where one group ends, the next one starts. That's why they join each other at the boundary value. So if this was 39.5, that is the boundary of the first group and the second group. Understand that?
Yes, sir.
All right. That's it. You can get up phones, man. Yeah, my order, I'm call them. You don't come already, so. Excuse me a second, guys. Zooming again, 10. Supposed to cover it. You put the different time. It's 9 persons, right? But it's 10, including Winston. All right, cool. All right, guys, sorry about that. So you see why we have to join the bars side by side on Histogram? Because where one interval ends, the other one starts at the exact same place. Get me? Understand that?
Yes, sir.
All right, good. But what we're focusing on now is on estimating the mean. So we want to estimate the mean. Now remember, mean is usually total something. So for example, you want the mean mass, it will be the total mass. It will be the total mass of all the balls divided by the number of balls, which is 37. The question is, how do we get this total mass? How do we get that total mass? If we don't know the actual mass of each ball. Because when they tell us that there are 12 balls in this group that measure between 35 and 39, we don't know the actual mass of the 12 balls because they gave us the data in a group. We don't know which ball measure 35, we don't know which ball measure 34.8, if any ball measure 39.1, if any ball measure 36, if any ball measure 34.4, 39.4. We don't know the actual measurements of the bars based on how the data is presented. We don't know. We have to do something to estimate the mean. Remember, we're estimating the mean. We can't calculate the actual mean. If we're going to calculate the actual mean, we'd have to know the actual mass measured by each ball. Based on how this data is presented, we don't have that information. So we have to estimate. We have to find some way of estimating what the mass, what the mean mass is. We need a total mass. We need a total mass. We need something to represent the total mass. We know so we divided by 37 already, you know. But how do we get the total mass? We have to make an assumption. We have to make a base assumption. All right. What is that base assumption? We're saying, okay, since the mass in this group can go from 35 to 39. Now let's put it exactly. Can go from 34.5 up to less than 39.5. If we assume that all the bars in that group measure the midpoint value, which is 37. So if we put the midpoint value as the mass of all the bars, what we're saying is that if some measure more than 37 and some measure less than 37, it's like them balance out each other. That's what we're trying to assume. But maybe all of them measure more than 37, and maybe all of them measure less than 37. I measure maybe more measure more than 37 than measure less than 37. Maybe none of them no measure actually 37. But in order to estimate the mean, we're gonna assume that all 12 bars measure 37, which is the midpoint value. So we're using this as our X value, the midpoint value, as our mass value, because we can't use a group value as a mass value. We want a mass value to be to use in order to calculate what the total mass of all 37 bars is. Understand that so far?
Yes, sir.
And then for the second group, we say, okay, this take mass from 40 to 44. We don't know the actual mass of all the bars. So here we're gonna do. We're gonna assume that all of them measure the midpoint mass, which is 42. We make all of them measure 42. Maybe none of them no measure 42. Maybe all of them measure more than 42. Maybe all of them measure less than 40. We don't know. But we have to make an assumption. You have to use a method. When I used to do CSEC maths, there was another method to estimate mean. They just call it the coded mean. Another method, but they change the syllabus for you to just use this method alone. So when I used to do CSEC maths in my day, a donkey years ago, right? We used to learn 2 ways of estimating the mean. 2 ways. But now they take out that original way and only using this way now, where you use the midpoint value. All right? So this is all one way you need to learn now. And I'm explaining the rationale behind it so you can appreciate it. For the next group, we're assuming it's 47. All of them measure 47. And for the next group, we're assuming all of them measure 52. These are all the midpoint mass value, midpoint values. The midpoint values. Because you're assuming that, okay, if you use the midpoint value, some measure more than the midpoint, some measure more than less than some measure less than the midpoint. So you're going to assume that all the bars in this group now measure 37, all 12 of them, which is not necessarily true. And then you assume that all the bars in this group, all 8 of them measure 42, which is not true either. It's not true. It's possibly, but it's highly unlikely that all 8 bars in that group, all of them measure 42. No. Just think realistically, it's not realistic. It's not just not realistic. It is possible, but just not realistic. It is not necessarily true. It is highly unlikely. Highly unlikely. It's almost impossible. Almost impossible. There's a slim chance that that is the case. Because you're randomly measuring stuff. It's a random thing. Understand? So you're not going to find that all of them measure 42. And the next group is 47. You're not going to say all 10 of them in the next group, third group measure 47. But you're assuming that for the purpose of estimating the mean. So you understand that so far?
Yes, sir.
Then we want a way now of adding up the mass of all the balls. Want to do it a nice, quick and easy way. And we have a table. I was talking, I use a table. So if we can do it group by group, so we want the sum of the mass now. We can multiply the frequency times the mass. Because the frequency is the number of them that measure that 42, 37, for example, 37. So you multiply the 12 and the 37. So you do 12 for this group, it's going to be 12 times 37. So if 12 bars measure 37, then the total mass of those 12 bars is 12 times 37. 12 times 37 is the mass of those 12 bars. You're adding up the total mass of all the bars gradually. So you do the first group first. Right? And that is 4, 4, 4. So the 12 bars in the first group have a total mass of 4, 4, 4. I assume that each of them measure 37. Understand that?
Yes, sir.
And then you have the 8 bars in the second group. You assume that all of them measure 42. 8 bars in the second group, you know. Yes, all right. You assume that all of them measure 42. So that 8 bars, I want the mass of all the bars, you know, but I'm doing them gradually. So the next 8 bars, the total mass of the next 8 bars is 336. This group is 8 times 42, which is 336. Understand that?
Yes, sir.
The next group has 10 bars. I will assume that all of them measure 47. Not true, not true, but for the purpose of estimating the mean, we're going to say, all right, make all of them measure 47 and see what would I get. If all of them measure 47, then the total mass in this group is 470. All the bars in that group is 470. So actually, it's like we measure 30 of the ball already now. 30 bars measured so far. We have 7 more left. Huh?
So, sir, you have to find the median to estimate it correctly, sir.
No, man, no reach median yet, man. Let us show you, man. Don't worry about the median yet, man. We'll soon come to the median. This is 10 times 47. 10 bars, each of them measure 47. The last group has 7 bars in it. 7 bars left to make the 37 bars. We have to measure the next 7 bars. Each of them measure 40, each of them measure 52. We're assuming each of them measure 52. So that is 364 is the total mass of those 7 bars. It is 7 times 52. So far, so good?
Yes, sir.
Yes,
So
sir.
if we add up all of these now, if we add up all of those now, that would then represent the total mass of all the balls. You understand? That would represent the mass of all the balls, right?
Yes, sir.
All right. So therefore, I'm going to add them up. And I think it came to 1614. Add up all of them. So it's 444 plus 336 plus 470 plus 364, which is 1614. So this represents the total mass of all 37 balls. We calculated it in a systematic way. So that represents the total mass of 37 bars. So if 37 bars have a total mass of 1614, it means that the mean of those 37 bars, the mean mass, this represents the mean. The mean mass of those 37 bars in X bar is equal to 1614 divided by 37. This up here is just the sum of all the balls. This is the sum of fx. And this down here is the number of balls. So this is the sum of the sum. This is like the sum of the sum. You're summing them group by group. Right? And that's how we do it now. So this was an estimated mean because we assumed that the mass that we use was a midpoint mass of a group. And it is not true that the midpoint mass of the group, it's not true that all the balls in a group measure the midpoint mass. It's not true. So for example, in the second group, it is not true that the 8 balls in the second group measure 42. It's not true. Not all of them measure 42, but we assume that they did to estimate the mean. And that is the reason why the mean is not a true mean, because we're not using correct information. We're using estimated information or assumed information. Think you can tell me now? Think you can tell me what now? Say to me, so what you would write in the exam? They ask you, why is this not a true mean?
Yes, sir.
All right, tell me then.
So it's an estimated mean because there's no specific mass for each number of balls for each frequency, so we use the midpoint of each mass to estimate the mean.
Okay. I have to say something which is not true. The data we use is not true. We use the midpoint mass of a group to represent the mass of the bars in that group. But you know that the mass of the bars in that group, not all of them measure the midpoint mass that we actually use. We use the midpoint mass in a group, but not all the bars in a group measure the midpoint mass.
Okay,
Right?
sir.
The bars in the group have different mass. They have different mass. And we're assuming that all of them in the group have the same mass, which is the midpoint mass, which is not true. Some of the mass them are going to be more than the 37. Some of them might be less than more, might be. Some of the mass might be more than the 37 in the first group. Some might be less than the 37 in the first group. Maybe none of them measure 37 in the first group. The possibility exists that none of them actually measures 37. But that's what we assume, that all of them measure 37 in the first group. So once you can explain or write something for that explanation, you're good. But important things for you to understand it. Because when you understand it, then when you start to write, you will say the right thing. Just what words you decide to use. So not everybody's gonna explain it the same way, using the same words. Because not like it's a definition that you learn in a book, like forces that which cause a body's state of rest to change, or you know, something like that. You know, like a definition that everybody know, that is in a textbook. Like Einstein write a definition and everybody just say the exact same way it appears in physics, or biology, or chemistry. Right? Not a definition. You put in something, a meaning into your own words. So everybody's explanation is gonna be different, but you still must mean the same thing, which is that we are using the midpoint mass of a group to represent the group, in that we are assuming that all the bars in a group measure the same mass. But that is not true. It is not true. We are not using the actual mass of the bars to calculate the mean mass. We are using an estimated mass, which is the mean mass for a group. And therefore, the mean is not a true mean, it is an estimated mean. All right, think we said enough about that, guys. Can we move on?
Yes, sir.
Is there anybody who don't understand it now? Is there anybody still don't understand it? Because they'll ask it in the exam, you know, guys. They'll ask it, I'm telling you, they ask. When we start with the past papers, you're gonna see that question. But they ask, why is it an estimated mean and not the true mean? And you're gonna see it for sure. All right. So let us continue. I know the exam question that I ask from time to time, and I tell you to ask that. All right. So let me continue now. So going back to the slide, see there, the midpoint and the sum column, work it out. Here's the formula, the sum of all the mass divided by the number of observations, and that's the mean mass. All right. So that is the mean, guys. That is the mean. So remember, I know the method you use is based on the data that you have. Remember, the key thing about the group data is that you don't know the actual data, right? You only know the group, right? So we're gonna take it a little bit further now. So now we're gonna look now at median, interquartile range, and semi-interquartile range. To do all of these, we need the quartiles, don't it? All of these relate to the quartiles, don't it? Remember, the mean is a quartile.
Yes, sir.
The interquartile range is the difference between two quartiles, Q3 minus Q1. And the semi-interquartile range is half of the interquartile range. And so to find those, we need the quartiles. But look here again, key thing again. We have to be estimating, because the data is grouped. I don't know the actual mass of the balls. As an example a while ago, you don't know the actual data. So we have to estimate. All right, so what is the method of estimating when you want to find the quartiles? Let's look at it. All right, let's look at it. So for group distribution, when the total frequency is much larger, so you have a large number of observations and a large number of different observations. Remember when the data was ungrouped? When the data was ungrouped, you know, we came up with a formula for calculating the position of the quartiles. The position of the quartiles. This is the position of the quartiles. And position. Keyword is position. Where is the quartile? Position of the quartiles. When the data was ungrouped, or when the data is raw, the position of Q1 was 1/4 of n plus 1, not it? And the position of Q2, not Q2 itself, the position where it is in the data, was half of the n plus 1 term. 1 term. That's where it is positioned. 1 term. And the position of Q3 was 3/4 of the n plus 1 term. That's when the data was raw. You could use that. When the data is raw, you can look at it and know that divide half and half and so forth. But when the data is in a table, that's what we use to calculate the position of the quartiles. Now, when the frequency is very high, you don't need, and you're estimating anyway, you don't need this +1 anymore. You don't need the +1 anymore. You don't need that anymore. You're not going to make any material difference anymore. So you can just say quarter n is the position of Q1, half n is the position of Q2, and 3/4 n is the position of Q3. We don't need to go the +1s anymore when the data is grouped and the frequency is high. So when the data is grouped, it's usually when you have a high number of data occurring at high frequency. And so you don't need the +1 anymore. And you are estimating anyway. So the +1 not going to make any material difference. So this is it. The lower quartile is the quarter n term, not quarter n plus 1 anymore. The median, position of the median is the half of the n term. So if it's 100, if it's 100 terms you have, then this is 25. Quarter of 100 is 25. And this will be 50. So the 50th term would be the median term. This is saying that the 25th term, if n was equal to 100, and 100 pieces of data, then the position of the first quarter will be the 25th term. And the position of the median second quarter will be the 50th term. And the upper quartile will be 3/4 of n. In that case, will be the 75th term. All right. And these are the position of the quartile. But here the important thing now, remember the data has to be ascending. Ascending data, ascending. That's when the data is ascending, going from smallest to largest. So these rules assume that the data is ascending, going from smallest to largest value. And if you notice, when they give a data in a table, it is always ascending. It's always from lowest to largest, from smallest to largest value, always. It's always from smallest to largest. The data will be ascending. All right? So the question is now, how do we find these terms when the data is grouped? And we don't know the actual measurements of the thing, the values. We don't know the actual, we don't know the actual measurements of the values in the table. How do we get it when the data is grouped? We have to do a cumulative frequency curve. You have to do a cumulative frequency curve. So simply enough, if you want to find median, interquartile range, and semi-interquartile range from group data, you have to draw a cumulative frequency curve. I'm going to attempt to, not attempt, I'm going to show you why you need a cumulative frequency curve. Why the need exists for you to draw a cumulative frequency curve. Remember, you're estimating. So I put the word estimated in red. You're estimating. Everything is estimating in group data. Estimating. All right, so it's a cumulative frequency curve is required to find these terms. The 25th term, the 50th term, the 75th term. For example, since the terms are an estimated frequency value, this curve, this smooth curve, is of a characteristic shape. The cumulative frequency curve is of a characteristic shape, which is called the Ogive. And CSEC asks us already, what's another name for the cumulative frequency curve? That word right there. The Ogive or Ogive, or I want to pronounce, but that's what it is spelled. Another name for the cumulative frequency curve is this. And CSEC asked that already in the past. I'm asking, I'm telling you. They asked that already in an exam. What's another name for the cumulative frequency curve? And that is the answer, the Ogive. All right. And is normally drawn.
Choice question, that's it.
Huh?
Multiple choice question, that's it.
Yes, yes. It was on a multiple choice paper. I remember it on a multiple choice paper. Yes. Yes, it was on a multiple choice paper. That is right. When I saw it, it was on a multiple choice paper many years ago. So anything that was set many years ago can be set again, right? Right, and it's normally drawn to show how many terms are less than or equal to any given value. Now, why do we need to show how many terms are less than or equal to any given value? You know why we have to go less than or equal to any given value? Because we don't know the actual values of the data. We only know how many terms. We only know how many terms are less than a given value, or we know how many terms are less than or equal to a given value. That's all we know. I'm going to show you on the table. When data is grouped, you will know how many terms or how many values are less than a given value. So therefore, because that is information that you know, you have to draw a graph that is representative of that information, which is a cumulative frequency curve. All right? I'm going to explain it more as we go. All right, so the cumulative frequency curve, cumulative frequency is placed on the vertical axis, but then the horizontal axis can use upper boundary values, it can use upper limit values, or you can use upper boundary values, depending on the information that you want. So when you draw a cumulative frequency curve, you put the cumulative frequency on the vertical axis. For the horizontal axis, you can either use the upper boundary values of the group, or you can use the upper limit values of the group, depending on the information that you want. And then there's going to be a difference. And I'm going to show you now. I'm going to show you what the difference is. And sometimes when you read a question, when you get a question, sometimes when you have to draw a cumulative frequency curve, sometimes you can read ahead in the question, like you read out the whole question first before you draw the curve, because then you want to know whether you must use the upper boundary value or you must use the upper limit value. But if you're in doubt, guys, if you're in doubt and you're not sure, use the upper boundary values, okay? Use the upper boundary values. These, use the upper boundary value. Let me erase that and circle it properly. If you're in doubt which one to use the upper boundary values. Use upper, yes?
Which one is the upper class boundary value, sir?
0.51. The one that was a 0.5. Yeah, the one that's a 0.5. The boundary values are the 0.5 values. The limit values are the values that you see on the table. When you use the upper boundary values, you are drawing a graph that shows less than. That shows how many observations are less than a given value. When
So,
you draw,
sir,
yes?
in the last one with the mass of the ball, sir,
We're
would
not
they?
drawing a cumulative frequency curve yet. We have an option to just trying to one.
Sir, I was trying to give an example to see if I understand.
Yeah. All right, go ahead.
So, sir, in the last one where we said the first one of mass kg 35 to 39, the limit value would be 35 to 39.
So this one will be the lower limit value.
Yes, sir.
Lower limit. And this will be the upper limit. So these are the limit values, lower limit and upper limit. The boundary now is a 34.5
And the
up
30,
to the 39.5. So the boundary, remember, you know, you see the boundaries, the boundaries are the same boundaries that you're gonna get on your histogram. They are gonna be the same boundaries when you draw a histogram. To draw a histogram, those values going at the boundaries. So the first one, for example, here, right here, will be 34.5. And right here will be 39.5. So those boundary values also form the boundary of your histograms, of your histogram. Understand? I remember where one boundary ends, the next group starts at the same boundary, right? Remember that? So these are your boundary values. Lower boundary, let's call it LB, and upper boundary, let's call it UB, upper boundary. So those are your boundary values. So I'm saying when you use the boundary value, it's always the upper you're using on the cumulative frequency graph. I'm going to show you just now. You're basically drawing a less than graph. You're drawing a graph that shows how many observations are less than. But when you use the upper limit values, you are showing how many values measure less than or equal to a given value. Less than or equal to a given value. All right, so boundary is less than, limit is less than or equal to. Now let me see if I can explain it now with an example.
So, sir.
Yes?
Sir, why it couldn't be 34.9 or and 39.1?
We're talking.
Sir, the upper boundary, sir. Why?
All right. Good question. Good question.
Sir, can I answer it?
Yeah, go on now.
Sir, it wouldn't be 39.1 or the other values, because when the next limit boundary comes, sir, it would be the starting of it. So the next limit value, sir, would be 40 to 44. So it couldn't be 39.1 that would come right before it.
Before the 40.
Yes, sir.
All right. So I hear what you're saying, but let me explain it this way. All right, let me explain it this way. So watch me now, Antoine. So when they give you this in the table, when they give you this value, when they give you that group in the table, that is taking values between 34, 35, and 39. Any value that is approximately 35, any value that is approximately between 35 and 39 can fit in this group. Anything. So watch me now. Can 39.1 fit in this group? Is this approximately 39?
No, sir, no.
Is this approximately 39 if you're to approximate it to the nearest whole number?
Oh, yes.
So measure 39.2. What that approximately equal to?
39, sir.
39.3, what that approximately equal to?
39, sir.
39.4, that's approximately equal to?
Sir, 39, sir.
All right. 39.446, what that's approximately equal to?
Sir, 39, sir.
39.48, what that's approximately equal to?
39, sir.
39.49, what that approximately equal to?
39, sir.
Now watch this now. 39. So all of them are approximately 39, don't it?
Yes, sir.
So all of them can fit in our group, don't it?
Yes, sir.
Good. So 39.5 now, what is that approximately equal to?
40, sir.
40. So anything will reach 40, anything will reach 39.5 cannot go in this group. That's why we say it has to be less than 39.5. Has to be less than 39.5 to fit in this group. See that? So once you reach 39.5, it's gone over into the next group. Because the next group starts at 40, you know. 40 to, what is it again? Add 5 to this. What is the code? 40 to 44. So, yeah. All right? So once it reaches 39.5, it's gone into the second group, it's not in the first group anymore. Again, that's why the value coming into this group, values coming into this group has to be less than 39.5. Once it reaches 39.5, it's gone. Look here now. This 39.49 is less than 39.5, you know, just less. But it fits in the first group there. Because it's approximately equal to 39 still, going to the nearest whole number. But once it reaches 39.5 here, it's gone into the second group. See that? And that is why for a value to fit in the first group, it has to be less than 39.5. That's why that is the boundary. But it is less than 39.5. You understand that now? Why it's up at 39.5, but we say less than 39.5. And then look at the other end of the spectrum now. The other end of the spectrum, and the other end of the range, is that we are saying this has to be greater than or equal to 34.5. Once it is greater than or equal to 34.5, it can fit in there, so. Because 34.5 is approximately 35, don't it?
Yes, sir. Yes, sir.
And anything greater than 34.5, but don't reach 35 yet, is approximately 35 still, don't it? Like, for example, 34.6, 34.7, 34.8. All of them values here approximate to 35. So anything from 34.5 up to 35 approximate to 35. So that's why these now are the boundary. This is the boundary values. This first group can take any value that is in that range that I've circled in blue. So you have the equal upon the end of the range here. We have the less than upon this end of the range.
So, sir, on the left right side of the range, sir, it's only lesser than and not lesser than and equal to, sir.
All right. So this side is always less than alone. And this side is always equal. Because this, remember, said start from 34.5, the halfway mark. You know? So you always have less than on the right side, but they have the equal upon the left side. Because if it becomes equal upon a side, it's gone into the next group. So it has to be less than 39.5.
Yes, sir, yes, sir, yes, sir, yes, sir.
Under the next group. All right, good. So back to the Ogive now. So the Ogive will always have this characteristic shape, right? All the cumulative frequency curve will always have this kind of shape like. All right? And those almost pass through the origin. Some of them start right here. Like start right here and go like so. Some of them will be flat like this. No. Some of them will go like so and be flat. And some of them will be straight up, more straight up like so. But it don't matter. All of them have this little S-ish kind of shape like that. All of them. Some of them flat, some of them tall. It all depends on how you set the scale. Some of them straight up, some of them kind of low. Or like so. Some of them go in between. Some of them more straight up. You see that? But all have that characteristic shape. All of them have this shape. Now what will happen is that these are your observations. And you always put your upper limit values. You can put the upper class limit, but you can also put the upper class boundary. So let's write or boundary, upper class limit, or boundary, or boundary. When you use the upper limit, you're doing less than or equal to. When you're doing the boundary, you're doing less than. So the graph will show how many observations are less than or equal to if you're using the limit, but it will show how many observations are less than if you're using boundary. All right, and then up here now, these are the actual these are your frequency. So if you measure in mass, so you measure in mass of balls. So you measure in mass of balls, and these are the balls up here. These down here have the lower, the balls down here have the small mass. And these are at the top, they have the large mass. The large mass, the bigger balls. That's why I said the data is ascending, right? Because you see, these are the mass. This down here, this will be the mass down here now. So that less than or equal to mass or less than mass. So these down here, this is a different color. It's black. These down here correspond to the lower mass, smaller mass value, while these up here correspond to higher mass value. All right. So once you get the curve, I'm going to show you how you draw the curve just now. Then that is the number of values. Always end with the total number of values, or total number of observations at the end. If it's 100 bars, up there says 100. If it's 37 bars, right up there says 37. Total frequency. The position of medium is right there. Half of n. So if it's 100, half of 100 is 50. So half n is the position of the median. Not the median itself, that's just the position. No, guys, you don't have the median values on the y-axis. You don't have them up there, no. Those are just the position of the median. To get the actual median, I have to come and you read it down here at the point. Down here is where the median is. And the median is a score, and these are your scores. These are your frequencies, down here are your scores. The data. All right? So we're showing the position of the median. Right there, the 1/4 of n is the position of Q1. So if it was 100, total frequency 100, position of Q1 will be the 25th. There were 100 balls. The 25th ball, 1/4 of 1 is 25th. The 25th ball would measure the first quartile mass. 3/4 n. So for example, there were 100 balls, 3/4 of 100 is 75. So the 75th ball, that will be the position of the 75th ball right there. And they want to measure the actual mass or the actual measurement, we read them down. See, they're reading the Q1 down. Down there is Q1 on the horizontal axis. So that is the first quartile value. Pay attention to the details. The quartiles are on the horizontal axis. Then you have a second quartile, which is also the median on the x-axis where the data is located. And it's estimate to estimating still. Then the third quartile will be right there. Position of Q3 is up there, and you read the mass of the position. You read the mass of the ball in that position. Talking about the mass of balls. Q3. And then from those now, you know, the median is Q2. The interquartile range is Q3 minus Q1. See them there? And the semi-interquartile range is half of the interquartile range. Basically, that's how you do it. All right? Now, a lot of people know how to do this, you know, but they don't have a clue about actually what is happening behind the scenes or why they do it. A lot of people can do these questions very well, get the right answer and everything, but they still don't know what is happening behind the scenes. They don't really understand what is happening. They just know what to do. I don't want that to be my students. I want my students to understand what is happening, because when you understand what is happening, if CSEC change the question a little bit or ask something that they have never asked before, because of your understanding of it, you will know what to say, you know what to do, you know how to approach it. I can't predict all the questions that they will ask. I can give you a lot of examples of questions that they have asked before, and I can maybe come up with some questions that they might ask. But maybe somebody might just come and just ask something different that they've never asked before. Now, if you just go off knowing alone and don't depend on understanding, then when they ask that unique question that they've never asked before, then you'll be at a loss. You don't need to be at a loss. What you need to do is understand it. So you must know it, and I'm not going to tell you that you must not know it, you must know it, but also it is even more important for you to understand it and understand what you're doing and understand the reason for it. The reason why they have to draw a cumulative frequency curve. What is the reason? Why do we do it? It comes back to the lack of information that we have, that we don't know the actual measurement of the balls. When we did the balls, the example of the ball, we don't know the actual measurement. But what we know, we can know how many balls measure less than any mass. And we can know how many balls measure less than or equal to the upper limit mass. So that's what you plot. You plot what you know. You plot a graph based on what you know. And therefore, because you plot a graph based on that information that you know, the graph will give you information of the same kind. So if you plot a graph to show, apples, or you plot a graph to count apples, and you want to know what number of apples would be, or if you plot a graph showing how many apples you get on a farm, on various farms across Jamaica. No, let's not say apples, let's say mangoes. If you plot a graph that shows how many mangoes a farm produced based on its size. So you take a sample of 10 farms and you say, okay, based on the size in terms of acres, or based on the number of trees on a farm, let's say number of trees on a farm and the number of mangoes that they get. And you say, okay, there's a direct relationship between the number of mangoes that they get and the number of trees on a farm, and you plot a graph. There might be a farm that was not in the data, you know. But you can use that graph to know approximately how many mangoes you're gonna get based on the number of trees that is on that farm, because you have a graph that shows that. Even though you're not capturing every single piece of data, you're using a sample. If you believe what the graph shows based on how the graph was plotted, because you plot a graph that says, okay, based on this size, based on the number of trees on a farm, you're gonna get this total number of mangoes from that farm. Then if there's a farm somewhere else that was not in the data, but then you know the number of trees on that farm, then you can put that number of trees on the graph, and the graph will show you how many mangoes you're supposed to get. So the same thing with the cumulative frequency curve. The information that you use to draw the graph will give you information of that kind for data that you don't actually know. You can use the graph to find information of that kind. So if you use less than or equal to mass to draw the graph, then the graph will give you back less than or equal to mass for what you don't know. If you use less than mass to draw the graph, then the graph will give you back less than mass for what you don't know. Right? So that's what it's all about. But I want to get into now explaining the information that you know and how you represent it on the graph. It comes back, as I said, to the fact that you don't know the actual measurement of the data when the data is put. All right? That's what it comes back. It comes back from that. So you have to use what you know. You have to use what you know. All right. So let's look at this one. So let's say this is the length of some leaves. I just draw this cumulative frequency graph as an example, right? So let's say this data shows the length of leaves. I mean, should have set it up so that it gradually give you what kind of gone ahead. All right. All right, so let me break it down for you. All right, let me take my time and break it down for you. I think we'll have to continue this tomorrow now. Maybe not get to do any other questions today because it's 12:30, Jared. No problem. We're not in a rush. We want to get it good and proper. All right. So these are the length of leaves. Let's say these are the length of leaves. They measure some leaves, you know, in a forest, and they put them in group, and it's 100 leaves. And leaves measure from length 1 centimeter to 50 centimeters. All right. But because there are 100 leaves, they can't list them 1 centimeter, 2 centimeter, 3 centimeter, 4 centimeter, all the way up to 50 centimeters. You're going to get 51 rows if you do that. So they put them in groups. So all the leaves that measure between 1 and 10 centimeters, they put them in the first group. And we still remember, this is still going from 0.5 up to 10.5, up to less than 10.5. So the boundary part of it stays the same, right? And then the second group is of leaves that measure between 11 and 20 centimeters. There are 24 of those leaves. Third group is those that measure between 21 and 30. There are 42 of those leaves, and so on, all right? So, same thing again. All the leaves in this group, there are 8 of them that measure between 1 and 10 centimeters, but we don't know the actual measurement of the 10. We don't know the actual measurement of the 10. But what we know? What we know is how many leaves measure less than or equal to 10 centimeters. We're using the upper limit now, we know. So we use less than or equal to upper limit. Right? We know that there are 8 leaves that measure less than or equal to 10, because everything that is less than or equal to 10 coming in this group, there are 8 of them. We don't know the actual measurement, but we know that 8 leaves measure less than or equal to 10. But understand that? Understand that, guys?
Sir, less than or equal to 10.
Yes, sir.
10 centimeters, yeah. Because any leaf we measure 1 to 10, we're using the limit values now. So we say less than or equal to the limit values. So less than or equal to 10 centimeters, 8 leaves. Because anything we measure more than 10 centimeters gone over another group. That's what we basically say. So all the 8 leaves in this group measure less than or equal to 10 centimeters. You agree with that?
Sir,
Yes, sir. Yes, sir.
Yes?
so this is the limit value, you said?
Yeah, I'm using the limit. See there? The upper limit. I'm using the 10. See all these values, are the same values I'm using over here. See them here?
Sir, when do we use the boundary limits, sir?
Use the boundary values. There's no specific, all right. You use the limit or the boundary based on the information that you're trying to get. So some questions will ask you for some less than or equal to information, and some questions will ask you for some less than information. But because we're estimating, really and truly, it don't really matter which one we use at the end of the day, you know. We're estimating anyway. The values will come out to be the same, almost the same at the end anyway. Right? So that minute difference between whether we use the limit values or the boundary values, not so important, not so critical. You understand me? So when you're in doubt, I'm saying to you, use the boundary values. If I was using the boundary value, this would be less than, look, this would be a less than right here. And I would put 10.5 instead, and 20.5, and 30.5, and 40.5, and 50.5. But then I would say, okay, I know how many leaves measure less than. Remember, I know the range. Remember the range of values here, you know, is from 0.5 all the way up to less than 10.5. So I know that everything inside here measure less than 10.5 if I was using the boundary values. Just like this slide was set up for less than or equal to. But we're going to do examples with less than just the same. You understand? So if we use a boundary value, we're going to say less than. If we use a limit value, we're going to say less than or equal to if we use a limit values. But we're going to do an example with less than just now. But I still want us to understand what this table is showing as we go. So we're saying the number of leaves that measure less than 10 is all the leaves in this group, 8 of them. And that's why the cumulative frequency is 8. So like we have 8 leaves, we have accounted for 8 leaves so far. So okay, how many leaves measure less than 20 in total? How many leaves measure less than 20 centimeters? All of these are measurements less than 20 centimeters. So it's all of these leaves, the 24 and the 8. All of them measure less than 20 centimeters. So that's what we know. We know the total number of leaves that measure less than 20 centimeters. So the total number of leaves that measure less than 20 centimeters is these. Sum of this and this, which is 32. So this row, this value is obtained by adding the 8 plus the 24 more to give me the 32. So we know that 32 leaves in all measure less than 20 centimeters, less than or equal to 20 centimeters. So we have accounted for 32 leaves already from the first 2 groups. Remember, when you're trying to put the leaves in ascending order from the shortest leaves to the tallest leaves, in ascending order. Then go to the next group of leaves. And how many leaves in all now measure less than 30 centimeters? How many leaves in all measure less than 30 centimeters?
Sir, it would be from the 1 to the 1.
All of those.
Yes, sir.
All of these. All of these, don't it? So
Yes,
you
sir.
know how many leaves measure less than 30 centimeters. That's information that you know. So you're gathering information that you know. That's what you know. You don't know the actual measurement of the leaves, but you know that 74 leaves measure less than or equal to 30 centimeters. The ones in here, the ones in here, and the ones in there. They go for the next set of leaves, which is the one that measure between 31 and 40 centimeters. And there are 21 of them. So when you reach 40 centimeters now, you know how many leaves measure less than or equal to 40 centimeters. All of these. The 74 we have so far, plus the 12 more, the 21 more, that give me 95 leaves now. 95 leaves. So I know that 95 leaves measure less than or equal to 40 centimeters. That's the information that you know. And then now, the last set of leaves, there are 5 of them. And how many leaves measure less than or equal to 50 centimeters? All the leaves, all 100 leaves measure less than or equal to 50 centimeters. 50 centimeters was the last one. So all the leaves, all of them, which is 100 of them. So this is the information that you know. So because that is the information that you know, that's the information that you can put on a graph. You can draw a graph that shows how many leaves measure less than or equal to any length by plotting these points. You plot these points. And after you plot these points, you draw the smooth curve through the points. That way you can find any interval. You can find any value. Like you want to find how many measure less than or equal to 15, you get it from the graph. You want to find how many measure 21, you can get it from the graph. Okay, you don't know it from the table, but you can find it from the graph by plotting what you know. You plot what you know. You know how many leaves measure less than or equal to 10. You know how many leaves measure less than or equal to 20. You know how many leaves measure less than or equal to 30. You know how many leaves less than or equal to 40. You know how many leaves measure less than or equal to 50. So because you're going to draw a graph that shows how many leaves measure less than any length, then you can use the graph to find that. That's how I put less than or equal to length down here, because that's what the graph is showing. How many leaves measure less than or equal to any length. So you plot these points that you know. Those 5 points. And then I bring my graph down to 0. I'll explain to you when we bring it down to 0. I'm not going to get into that just yet. I'll explain that soon to you afterwards. But you plot these points. Plot those 5 points. Those are the 5 points. And then we bring it down to 0. So that's a point down here. And I explain that point down here just soon, but I'm not getting into that just yet. All right? That's what we have so far, guys. So this graph then will show you how many leaves measure less than or equal to any length you want. If I want to know how many leaves measure less than 22, just come right here and find 22. Go up on the graph, read it across, and it will tell me approximately how many leaves measure less than or equal to 22. Understand? Less than or equal to 22. If I want to know how many leaves measure less than or equal to 36, I come 36 right here, so I want to know how many leaves measure less than or equal to 36 centimeters. I come on the graph, that was not one of the points, and I come across and I read it here, so it tells me approximately how many leaves measure less than or equal to 36 centimeters. It might be 91. So I know that 91 leaves measure less than or equal to 36 centimeters. But I can also read information the other way. I can know what is the approximate length of a leaf. That is, these are the number of leaves, you know. And these are the shortest leaves, these are the tallest leaves at the top. So I can say, okay, what is the length of the 30th? What is the length of the 45th leaf? These are the leaves, you know, you're counting them up this way. What is the length approximately of the 45th leaf? So I can come and find 45 right here. This will be 45. 45. I go across on the graph and I read it down. And I get that measurement that look like I'm maybe around 20, 24. So I can approximately 45th leaf approximately is 24 centimeters long. I'll put another way. 45 leaves measure less than or equal to 24 centimeters. 45. The 45 leaves down here. All of them measure less than or equal to 24 centimeters. So the graph is tell you how many leaves measure less than or equal to any length that you want. That's what this graph is showing. Why? Because it was drawn from that information. It was drawn from that information because that's all we can know. We can know how many leaves measure less than or equal to any length because we don't know the actual length. But we know how many leaves measure less than or equal to any length. Then know if I want to find my median, because there are 100 leaves in all. And the leaves are now in ascending order from the shortest leaves down here to the tallest leaves up here. They are in ascending order now. This is how I plot the graph. If I want to find the median length, then I find the 50th leaf. These are the leaves, you know. These are the leaves. There are 100 leaves in ascending order. So the leaves are in ascending order from shortest to tallest. Then the one in the middle is my median leaf. The one in the middle has my median length. The 50th leaf has the median length of the leaves. The median length, the 50th one, the one in the middle. So I come across and I read it down here, so, and that will be my Q2. If I want to find the first quartile length of the leaves, I know that the 25th leaf, because it's 100 leaves, the 25th leaf is 1/4 of 100. The 25th leaf is right here. I want to know the length of that leaf. I come across on the graph and I read it down here. That is Q1. If I want to know the upper quartile length of the leaves, so I know that the 75th leaf, the length of the 75th leaf is the upper quartile length. So I go on the graph and I find the 75th leaf, because 75 is 3/4 of 100. There are 100 leaves in a straight line from the shortest one to the tallest one in ascending order. And I want to find the upper quartile length of the leaves. I need to find the 75th leaf in the line. So I come up on the graph and this is the 75th leaf. I come across on the graph, read it down, it tells me the 75th, the length of the 75th leaf. And that is the upper quartile. But that is done for you on the graph, guys. See there? I'm finding the median length now. See there? Q2. Look at the graph. Corresponding to the 50th leaf in the line. Then the lower quartile, 25th, because it's 1/4 of 100. If it was 80 leaves, 1/4 of 80 is 20. So I find the 20th leaf. If it was 80 leaves, then the median would be the 40th leaf. 40th leaf would have the median length. So you'd have to find the 40th leaf. If it was 80 leaves, then you go to 3/4 of 80 is 60. So the 60th leaf would have the upper quartile length. So you'd have to find the 60th leaf on the y-axis. The leaves are on the y-axis, the lengths are on the horizontal axis. So you come down and read the Q3. And that is Q3. And once you find those quartiles, then you can calculate, you can see what the Q1 is 17, Q2 is 24, which is the median, Q3 is 31. And then from that, you can find the interquartile range and the semi-interquartile range. So this is a simple example. This is a simple example of it. Now, in addition to finding median and interquartile range, you can also find, as I said, measurement of data, how many data measure a certain length. And what length is the number of data less than or equal to. You can find additional information. I'm going to practice some of those questions, finding additional information from cumulative frequency curves. So it's not just about finding median and quartiles. It can be used for other things. That's what is okay. So we're gonna deal with that soon. But I want to talk about range first. We're talking about range. So notice, since we came onto ungrouped data and group data, we have not spoken about range. We spoke about mean, mode, median. Oh, by the way, when the data is grouped, I'm going to deal with mode for group data just now. So don't worry, I'll come in. range. So the definition for range is not just largest value minus smallest value anymore. Once the data is grouped or the data is ungrouped. Once the data is presented in a table, it is no longer considered raw data. It is considered either ungrouped data or grouped data. Whether the data is raw, whether the data is grouped or ungrouped, the range is calculated the same way. It is the upper boundary of the largest observation minus the lower boundary of the smallest observation. In other words, you're going from the lowest boundary value all the way up to the highest boundary value for the entire data. You're going from boundary value, smallest boundary value in the first group to the upper boundary value in the last group. That is a range. See there? Upper boundary of the largest observation minus lower boundary of smallest observation. That's how we calculate the range when the data is grouped or ungrouped. Now, I'm here to tell you that I've not seen any question asked for range when the data is grouped or ungrouped. I don't see it yet in an exam question. They only ask for raw data so far. But I still wanted to know it just in case. Everything important. All right, and this is it. So we're talking about the mass of some stuff again. We're using the data as ungrouped now. So some persons ask them to calculate the range from this data. Ask us to calculate the range from this data. They might just want to say 52 minus 37. Remember, this is measurement data, and so that 52 here, a 52 here can take values less than 52.5. But greater than or equal to 51.5. So it means that any value up to 52.5 can, up to less than 52.5 can be used as 52. That's what I'm basically saying. Any value that is less than 52.5 can be fit into this group as approximately 52. All right, but still greater than 51.5, as I said. So that group takes value up to 52.5. And then this first group here so takes any value from 36.5. Any value from 36.5 can go in that group. So therefore, the range of this data really is between these two values. That becomes the range of the data, 52.5 minus 36.5. For the first group, the first value 37. If something measures 36.5, it can be used as 37. And if something measures less than 52.5, like 52.4, it can be used as 52. So the range, therefore, is between 52.5 down to 36.5. So that is the range. All right, that is the range. Come on, come on, come on. See there? 52.5 minus 36.5. And it's the same thing if the data was grouped. Because the data was grouped, a value up here for this, let me use a different color. For this one can take values that are less than 54.5 and a value up here that is greater than or equal to 34.5 can fit in the first group. So your range really is from this value all the way up to this value. That's where the data value is set. Can go from 34.5 all the way up to less than 54.5. So the range of your data, therefore, is 54.5 minus 34.5. It's the range of the data that can fit into this data. So that is the data range. Understand that, guys?
Yes, sir.
Remember, you know, guys, you're not going to see this in the past paper, yeah? So we might not mention this again because we're going to be practicing from past papers and they don't set this in the past paper yet. And the data is grouped or ungrouped. So you have to remember it from this one example. You have to remember it from this one example. The only time you use largest value minus smallest value is when the data is raw data. But once the data come as measurement data in a table, especially as measurement data in a table, because anything that measures less than 52.5 is approximately 52. And anything that measures 36.5 is 37, taken as 37. It means that the data range is from 36.5 up to 52.5. That's for the first one. For the second one, anything that measures 34.5 can fit in the first group, and anything that measures less than 54.5 can fit in the last group. So the data range really is from 34.5 up to 54.5, and therefore that is the range, the difference between those two values. So it's always largest upper boundary observation minus smallest boundary observation. That is what gives you your range when the data is grouped or ungrouped, and especially when it is measurement data, not counting data, measurement data. But go to that. But okay with that?
Yes,
Yes,
sir.
sir.
Yes, sir.
All right, let's move on. Telling you everything, you know, we don't want to come in the next. The statistical diagram from group data. First one is the histogram. We're going to do some examples. In fact, tomorrow I think I'm going to set up a nice example for you. We're going to do. All right. So when you draw a histogram, the class midpoints are used to represent the classes and are plotted on a horizontal axis. The width of the bars are equal. Right? They don't have to be equal still. No. You can have a histogram with the width, them not the same. But I think at CSEC. All right, so a histogram can be drawn such that the data are represented by the area. But for CSEC, they tend to make the bars, the width of the bars the same. And the width of the bars must be equal to the class width of the group. See there? The width of the bars must be equal to the class width of the group. The width of the bars must be equal to the class width of the group they represent. And then the height of the bars will be the frequency. So the important thing to remember for the histogram, as I told you before, somebody tell me the important thing. Tell me what I said was important to remember about drawing the histogram. Somebody tell me if you're listening.
Repeat, sir.
What is the key thing to remember to do when you're drawing a histogram?
So they have to be side by side.
And they're side by side at what value?
0.5, sir.
We call those 0.5
So the
values.
boundary.
Good. The bars of the histogram, they're joined side by side at the boundary values. That's a key thing to remember. The bars of the histogram, they go from boundary value to boundary value and they join side by side at the boundary value. And then the height of the bars now is the frequency. That's all you know. So it's almost like you're drawing a bar chart, but you draw you put the bars side by side. And you always want to make the scale of the graph match the width, the class width. So you want to make the scale of a graph match your class width, so it's kind of easier to draw the histogram. But you want everything to be symmetrical. So the width of the bars must match the class width, and you draw the bars boundary value to boundary value such that the midpoint of the groups will correspond to the middle of your bars. The midpoint of the groups will correspond to the middle of the bars. All right, we're going to practice it until you see. That's telling us stuff, right? So for that data, let's say I want to draw a histogram for that data. Those are my midpoint values. So the middle of the bars must match those midpoint values. The middle of the bars will match those midpoint values. All right, so and then the height of the bars is the frequency. The height of the bars is the frequency. So that will be a histogram for that data. But in terms of boundary values, this boundary with 2.5, draw it in red. This boundary right here with 2.5. This one ends at 2.5. And this one starts at 2.5. Right? So the next one, the next boundary would be, what is that now? 5.5 from this group. 5.5. This group ends at 5.5. This group ends at 5.5. So that's will be 5.5 right here. And this group ends at 8.5. That's will be 8.5 right here. 8.5. The next group ends at 11.5. This one will be 11.5. This one ends at 14.5. So this will be 14.5. And the first one is not really 0.5, you know. If this is going up, yeah, look at it this way. If this is going up by 3, then the value up here so will have to be -2. And up here, let's do this way. Going up by 3, right? Going up by 3, the value before this would have been -1. The next boundary should be -1.5. This really should be -1.5. -1.5. All right, we're gonna do a better example. But the bars go from boundary value to boundary value. This one was just focusing on the midpoint though. That the midpoint must be in the middle of the bars. The midpoint must correspond to the middle of the bars in our cases. These are the midpoint values. And then the height of the bars is a frequency. So the height of the first bar is 2, see there, 2. The height of the second bar is 5, see there, 5. The height of the third bar is 23, see there, 23. Height of the fourth bar is 17, 17. The height of the last bar is 8, 8. So the height of the bar corresponds to your frequency. The bars go from boundary value to boundary value. That's the first one I'm showing, the statistical diagram. So when I practice someone, yes?
So for normal graphs, sir, we would normally put the values that are on the x-axis to be the value that it's supposed to represent, sir. But for histograms, we use the midpoints.
No. All I'm saying to you, when you draw a histogram, right?
Yes, sir.
The midpoint value must correspond to the middle of your bars. The next thing is that the bars join side by side at the boundary values of the groups. That's what I wanted to point out to you. It's not a value you put in. Remember, there's a range of value you put in. The histogram, all right, let me show you this way. All right, so remember this group, the second, let's use the second group. The second group, if we focus on the second group, right? The second group goes from 2.5 up to 5.5, you know. So you join a bar from 2.5 up to 5.5 for the second group. See there? From 2.5 up to 5.5. That's how wide that bar is. The data in that group is that wide. And then the frequency is 5. So it comes to a height of 5, matching the 5 out here. So the width of the bar matches the width of the data that can fit in it from boundary value to boundary values. And the bars of the histogram match the boundary values of the data. So the bars go from boundary value to boundary value just the same. Understand that now?
Yes, sir.
Yes, sir.
All right. So it's not one value represented, but it's just that it's going to end up being such that the middle of the bars would then also correspond to the midpoint values. But you can actually draw a histogram without putting in midpoint values. Just draw it from boundary value to boundary value. Just plot the boundary values. Just plot where the boundaries are. And you get it. The midpoint will automatically be in the middle of the bars. All right. So that is the histogram. The next thing we can get is a frequency polygon. And just like when we did ungrouped data, the midpoint of the group, the frequency polygon is like a plotting points. But when you've drawn a frequency polygon from group data, you have to use the midpoint with the frequency. All right, you have to use the midpoint with the frequency. That's what this is saying. The midpoint is used to represent the group and are plotted on the horizontal axis, and you plot the frequency on the vertical axis. And it's going to correspond to the top of the middle of the bars as well. The polygon must be drawn and closing the two ends. Remember, always close the two ends. You see it here now, we're going to use the midpoint and plotting like midpoint against frequency. We're plotting a frequency polygon. Those are the points at the top of the histogram. Join them, straight lines. I move the histogram, then that is just a line graph for now. What you do, you go to the value before first value, which will be down here, and put it down to 0. And the value after the last value will be here, and put it down to 0. You draw this end down to 0, and draw this end down to 0 to close it. You have to close because it's called a polygon. A polygon is a closed shape. So put in those values before and values after, we bring the frequency down to 0. The reason why I bring the frequency down to 0, guys, because they were not represented on the table. So the value out here was not represented on the table. All right, it was not represented on the table. That's why I bring it down to 0. So, and then you close the two ends. Close the two ends of the polygon to make it a closed shape. That's polygon, frequency polygon. Now we'll come to the cumulative frequency curve again. So now we're going to look at how we can use it as an example to get additional information. All right. And if you notice this one now, I use less than mark. So I'm going to use as an example of how you can extract additional information from a cumulative frequency curve, because sometimes what they'll do, they give you a cumulative frequency curve in the exam and you have to get information from it. But first, you have to understand what it shows. Now, how I know this one is a less than? How can I look at it and know that this one is less than? If I didn't see the less than down here, sometimes I just put marks, you know. How could I know that it's a less than and not a less than or equal to? All right, let me tell you how I can know. Because I see the points are at the 0.5. Is it 10.5? 15.5. The points are at the 0.5 marks. They're not at the limit marks. If it was right here at the 5 now, then I know that is the limit. And to be less than, it will be just less than or equal to. But I can see the points are a little bit over the marks. So it's at they are 0.5. So they're using boundary values. So once they're using boundary values, it becomes less than marks. All right, so let's read what they said. So a cumulative frequency curve, in addition to finding the median, interquartile range, semi-interquartile range, the Ogive can be used to find how many terms are above or below a given value. And it can also be used to calculate probability of selecting a group of values. It can be used for probability. It can be used to find how many terms are below or above a given value. And it can also be used for for probability. So an example here. And this example shows the cumulative frequency graph for the test marks obtained by some students. So that's what the graph is showing. The test marks obtained by students. You know, some students are going to get low marks, some students are going to get high marks. The students with the low marks are the ones down here. They get the low marks. The students at the top are the ones with the high marks. They get the high marks out here. That's what the graph shows. The data is in ascending order. So these are the students. The ones who get the low marks, the ones who get the high marks at the top. And then down here are the marks. But it shows how many students show less than a certain mark. Why? Because the data this will come from group data where you don't know the actual marks obtained by the students. So you can only draw a graph to show what you know. You can only draw a graph to show how many students score less than any given mark, because that's what you know. All right, so let's answer some questions. So because I say less than marks, I know that I'm using the boundary limit values, the boundary values. All right, the boundary values I use. How many students in the survey? How many students did the test? Based on this graph.
40, sir.
40. But remember, these are the students, 40 of them in a line. In a line from the lowest to the highest. From the lowest, the ones who get the lowest marks to the ones who get a high marks at the top. And this tells me that there are 40 students, because the last mark is up at 40. So there are 40 students. All right, go to the answer. There's 40. Next question is, how many students got less than 18 marks? So I can find how many students scored less than 18 marks. I can find that out. How many students scored less than 18 marks? What can I do?
Sir, you put in the 18 marks on the X axis, sir.
Let's find 18 down here. So. Because the graph is already showing me how many students score less than any marks. If I want less than 18 marks, I'll just find 18 down there. Come up on the graph and read it across and I get the number. All right, simple as that. So tell me that 35 students scored less than 18 marks. 35 students scored less than 18 marks. See here? Oh, I know. Look at it. All the students down here corresponds to all the marks down here. It represents this part of the graph right here. These are the marks. All of these marks are less than 18. And these are the students. All of them, 35, the first 35 students in the line. All of them score less than 18. 35. So how many of them score more than 18 then? How many of them score 18 or more? If 35 students score less than 18, how many scored 18 or more?
5, sir.
5 at the top. Good. 5 at the top.
5, sir.
That's 35. Next question. How many students scored more than 9 marks? How can I find how many students scored more than 9 marks, approximately?
Sir, then just find the 9, sir, on the x-axis.
And then?
And then draw it up to the blue curve line, sir. And then draw it across.
And then?
And then across to the
find the 9. Find the 9. Draw it up to the graph. Go across, and I get 10.
Yes, sir.
So what that mean? What does 10 mean?
Sir, subtract the 10 from 40 and get 30, sir.
The graph shows how many students score less than a certain mark. This time I want to know how many scored more. So what this is saying is that 10 students, this is actually saying that 10 students scored less than 9 marks. We want to know how many scored more than 9 marks. So that must be the rest of them. So it's 40 minus the 10. The rest of them scored more than the 9 marks, approximately. So that's 30 of them. There. 30 of them. 30 at the top up here. 30 up here. All of these down here score less than that mark. All right. Next question. The number of students who score between 9 and 18 marks approximately. Between 9 and 18 marks. Okay, I'll find how many students score between 9 and 18 marks.
Sir, just minus the 35 from 10.
Oh, yeah, man, that's it. Because these are the marks between, represented by this part of the graph right here. Correspond to the students between here and here. So the student between the 10th one and the 9th and the 35th one. So approximately it's 25. All right? Approximately it's 25. One between the 3rd, the 10th and the 3rd and the 35th. Approximately 25 students. All right? Next one. Probability that a student scored between 9 and 18 marks. Probability that a student scored between 9 and 18 marks. What did that be? Remind us, 25 students score between 9 and 18 marks, you know. And there are 40 students in all in the class. What's the probability of getting one of those students who score between 9 and 18 marks? 25 of them. Probability.
Sir, 1 over 25, sir.
Huh?
Sir,
No,
1 over
what
25.
No, what is probability? Probability is the number of outcomes that you want divided by the total number of possible outcomes. If you're selecting a student randomly from the group and you want him to score between 9 and 18 marks, how many students score between 9 and 18 marks?
25.
25, sir.
25. And how many students are we selecting from?
40, sir.
So the probability is 25 out of 40. But if you're selecting from 40 students, it's only 25 you want. So the probability of getting one of those 25 is 25 out of 40. So that's it, 25 out of 40. All right. Now listen to this now. What is the pass mark if 12 students pass the test? What is the pass mark if 12 students pass the test? So the first question is, if 12 students pass the test, where are those students located on the graph? Remember, these are the students up here now. Where are those 12 students up here? Where are they?
So, sir,
Students.
since you give it a number of students, sir, you can just.
No, listen to the question. No. Answer the question I ask you. I said, first thing, go step by step.
Yes, sir.
If 12 students pass the test, where in this line would you expect those 12 students who pass the test to be? Where would they be?
12 and above, sir.
I mean 12 and above. These are the students. There are 40 students who did the test. Only 12 of them passed the test. Where on this graph, where on this line are they? Remember or not? These are the students in ascending order from the ones who get the low marks, the ones who get the high marks. Because the data is in ascending order. So the data is in ascending order from, right? So the on the y-axis are the students who did the test, but the ones who scored the low marks at the bottom and the ones who scored the high marks at the top. And the question is, where would these 12 students who passed the test be?
Sir, Ebert said over 28.
So the top 12, man, top 12, right? Top 12. All right, I'll put it another way. All right. So if 12 students pass the test, if 12 students pass the test, it's not coming out. Not AY doing its own thing. Okay. If 12 students pass the test, how many failed?
28.
28. So therefore, you can look at it two ways. If you want to pass the test, you have to score more than what the 28 students get, don't it?
Yes, sir.
It means that 28 student also fail, 28 students fail the test, don't it? If 12 students pass the test, it's the top 12 pass the test. So it means that the 28th student failed the test. Agreed?
Yes, sir.
Because 28 plus 12 is 40. So if 40 pass it, if 12 pass the test out of the 40, then it means that the 28 students below them fail the test. So if you want to pass the test, you have to score more than what the 28 student got, don't?
Yes, sir.
Or you can go from, you can score what the 29th student got. Because from the 29th student up to the 40th student, those are the 12 that pass the test. So the first one that passed the test is the 29th student. So that's another way we can do it. But most people would subtract 40 minus 12 and get 28. And so, okay, if you want to pass the test, you have to score more than what the 28 student get. Right? Top 12 students. So basically, the pass mark is equivalent to what the 28 student got. In other words, you have to score more than what the 28 student got to pass the test. You see there, find the 28 student on the graph. See him up here now. I'm finding him up here, 28 student. Come across on the graph and read it down, and it says 14 marks. So the pass mark is 14 marks. Once you score 14 marks or more, you pass the test. Remember now, 28 students would score less than 14 marks. So to pass the test, you have to score more than 14 marks. So something like that. As an estimate, you know, so it's an estimated answer. So that is it. You can understand what we did on this graph, guys? You can understand?
Yes, sir. Yes, sir.
Yes, sir.
All right. I want you to watch over the video, right? Watch over the video. But I want to just finish off the notes today. And tomorrow I'm going to do a lot of examples with this thing. All right. Who knows? This is where we reach tomorrow. We might do some more examples on Wednesday. So I want to do the classwork on Wednesday, but maybe I need to do some more examples because this is a wide topic. All right, because you have raw data, group data, ungrouped data. But let's look at how you find mode from group data. And see the keywords here, you have to do a construction to find the mode on group data. Now, I think it's only one time I ever say a CSEC question asked you to find mode. They ask for the mode or class all the time, but they don't normally ask for the mode. So you have to do a construction. So you have to remember this, guys. You're not going to see that in the past paper. All right? You're not going to see that in the past paper. I think that's it many, many years ago. Not in recent times. And since we're going to be practicing with the more recent past papers, you're not going to see it. So you have to remember it from this one example I want to do. All right. So to draw the mode, to find the mode, you have to construct a histogram. You have to construct what we call modal class diagonals to find the mode. All right, so let's look at it. The mode of a group data is located in the modal class. And CSEC will ask you what is the modal class. The modal class is the one with the highest frequency. So the class with the highest frequency is a modal class, and the mode will be one of the values in that modal class. The mode has to be constructed on a histogram as shown in the following example. So to find the mode, we have to draw a histogram for the data. And then after we draw the histogram, we have to do what we call the modal diagonals in the modal class to estimate what the mode is. All right, so let's look at it. So let's say we're using that same set of data that we had before. And that's the modal class, guys, one with the highest frequency. So the question asks, if the question gives you this set of data, and they ask what is the modal class? One with the highest frequency is 23. So this is the modal class right here. Modal class. Because it corresponds to the highest frequency. It's going to be the tallest bar on the histogram in draw it. Right? So that's it. The modal class is 6 to 8. If those is kilograms, this is 6 to 8 kilograms. That's the modal class. And 6, you like to ask that. What is the modal class? What I don't ask a lot is the actual mode. So look at this data now, guys. The modal class is 6 to 8. But the frequency is 23. Now, right across from 23, you have 17 down here. That is between 7 and 11. And you have 13 down there. That is between 3 and 5. What value would the mode tend towards? Would it tend towards being closer to this group or closer to that group? Which one? The mode is a value between 6 and 8. You know? Will it be closer to the 6 in that it is closer to this group, or will it be closer to the 8 in that it is closer to this group? Which group will it be closer to? The value, the mode. Closer to the 6 or closer to the 8? The mode. Anybody can tell me? All right, it's going to be closer to this one. So it's going to be closer to the 8 because this has more values with these. More values between 11 and 12. So the mode is coming closer to this end. Right? So the mode is not going to be 7. It might be 7.5. Not going to be in the middle. The middle value between 6 and 7, 6 and 8 is 7. But because this group up here is greater than the one below it, it's going to be closer to the one above. All right. So see here, we're going to draw the histogram again. All right, so draw the histogram. So when you draw the histogram, guys, this is the modal class, the one with the highest bar. This one is the modal class. All right, I want to watch out the video later now. It's a modal class. And see, if you notice this bar beside it, no, not ready for that as it. Not ready for that as it. This bar that comes afterwards is taller than this bar there. So it means that the mode is not going to be in the middle. It's going to be more to the right, closer to the taller bar. Right? The mode is going to be more to the right of the middle. And to find how far to the right of the middle, we construct the diagonals across here and there. like so. Look, bam. Construct a diagram from upper left corner to the top of the adjoining bar, and from the top right corner to the top of the adjoining bar there. So if you notice, where those two red lines intersect is more to the right of the middle line. So this is the middle line, but they intersect more to the right of the middle line. That means that the mode is right there, to the right of the middle line, which is 7. That's how you do the mode. So to do the mode from group data, you have to draw a histogram. After you draw the histogram, you go on the tallest bar and do that diagonal thing there. From the top right-hand corner to the top of the bar before, to the top left-hand corner to the top of the bar after. Where those two diagonal lines intersect, you plot down on the graph to find the mode. That is the mode from group data. I think that's it. I think we'll finish right there. This is 7.4. The mode. I think we'll finish right there with the notes. But I'm not going to pressure you today. I'm going to start by the class tomorrow and go straight into examples. I want you to watch over the video today of all that I've said. I'm going to start back tomorrow's class with some examples, some primitive frequency graphs, some group data and stuff tomorrow. That's what we're doing tomorrow. Just use today, look back over the video, listen to what I've said, listen to what I've explained today. All right. Try and see if you can understand. If you don't understand something, you can send me a message. All right. But that's what I wanted to do for today. And tomorrow, we just come and practice examples from past papers and also from the handout. All right, guys. Promise me you're gonna do that.
Yes, sir.
Yes,
right.
sir.
Make sure
Sorry,
you watch
what do you
over
want
the
us to say?
Huh?
So you want us to re-watch the video?
I wanted to watch over the video to listen to all the explanation that I gave, the reasons, and to get that detail, and then tomorrow I'm gonna put it all together by practicing some questions. Especially what I wanted to understand is how the cumulative frequency graph is drawn and the reason you draw it that way with respect to the information that you know. You only know how many is less than or equal to any value, or you can use less than a value. And so that's what you have to draw, and that's information therefore that you can get. If you use a certain information to draw a graph, then the information that you get from it is similar kind of information. All right, so that is it. So I'm gonna end it there for today. I'm gonna start back tomorrow with the example. Just watch over the notes for me, watch over the video for me, please, before tomorrow's class. So we can make the session tomorrow a lot easier. All right, guys.
Yes, sir.
All right then. All right, very good.
Yes, sir. Tomorrow.
Very good. All right.
Later, sir. Later, everyone.
All right. Bye bye,
Hi,
everybody.
sir.
Bye bye. Bye
Tomorrow,
bye. Bye bye. Okay. Okay. Bye.